Hello, welcome to my talk all about fluids. This talk is on turbulent boundary layer, in which I will show how the standard turbulent boundary layer is derived, and some details within the turbulent boundary layer will be discussed. This development is very useful for practical purposes, as well as for providing the basis for developing the enhanced or improved turbulent boundary layers for different applications. Why we need to study the viscous boundary layer? In principle, the full solution to the Navier-Stokes equation would be only use the direct numeric simulation, DNS, which would resolve all ADs from the largest to the cosmograph length scales. A requirement for this direct solution is the number of the grid, which in principle is proportional to power of 9 divided by 4 of the Reynolds number, and this can lead to a huge number of grids if the Reynolds number is large. As deduced by Sparat in 2000, DNS would be ready for practical application in around 2080 if the advancing speed of computer technology can be maintained. Take an aeroplane or a car as an example. The grid needs for length is 10 power of 7. For LES, it's 10 power of 11.5, and for DNS, it is 10 power of 16. Currently, we are pretty much in 10 power of 9. However, in 2016, he and his co-author revised the claim and stated, by now we are not confident of this for the 21st century, or even that it will ever happen. We know for the viscous flow, an important aspect is to calculate the skin friction drag accurately, which is a challenge so far for numerical modeling. The most popular method, the length modeling, which has the least requirement on grids, would have issues with the grid generation in the boundary layer. Since for good modeling, a requirement would be that there must be points within the wall unit y plus equaling to 5 or less. This requirement would lead to a very large number of grids for length modeling. Another issue is in the boundary layer, the complicated processes are involved in the transition from laminar to turbulent, from low Reynolds number to high Reynolds number. Relatively, the confidence of the turbulence modeling is high only for the flows of high Reynolds number. In reality, the modeling of the near wall flow would be made often use the wall function, such as in the commercial software and in the open source. This avoids the reservation of the boundary layer directly. In this regard, the understanding of the boundary layer would be very important. Turbulent flow can be simply regarded as the superposition of the highly irregular and oscillatory flows upon a smooth flow. More specifically, the superposition of the fluctuating flow on the mean flow. However, an accurate definition on turbulent flow would be difficult, probably because it is too difficult to use few words to describe the extremely complicated phenomena from case to case. Generally, turbulent flow happens when the Reynolds number are large enough. For instance, in a horizontal circular pipe, the critical Reynolds number is 2,300, while in the boundary layer on a flat plate, it is 500,000. This can be seen from the free online book, Fluid Mechanics, Turbulent Flow, and Turbulence Modeling by L. Davidson. If we look at the physics of the Reynolds number, we can see the Reynolds number is actually the ratio of the fluid inertial force over the viscous force. In this regard, it can be understood that the turbulent flow occurs when its inertial force dominates the viscous force. There is a similar statement in Wikipedia on how the flow turbulence is caused. Turbulence is caused by excessive kinetic energy in parts of a fluid flow, which overcomes the damping effect of the fluid's viscosity. However, how a turbulent flow starts is really unclear and still challenging too. Having difficulties in defining the flow turbulence, there are some common characteristics for the turbulent flows. These include irregularity. This is very obvious when we compare the turbulent flow to a laminar flow. The fluctuating part is always unsteady and chaotic. Diffusivity would be significantly increased in turbulent flow, and this would increase the resistance and heat transfer too. Hence, in some practical application, turbulence is enhanced to increase the diffusivity in the flow. Turbulence flow always happen in large Reynolds numbers. For instance, in paper flow, it is 2,300, and in the boundary layer flow, it is 500,000. Turbulent flow are always three-dimensional. However, in the 2D setup, the mean flow may be two-dimensional, but the fluctuating flows are always three-dimensional. Dissipation. The turbulence would increase the energy dissipation. This is different from those in laminar flow, in which the dissipation happens in the molecular scale. In turbulent flow, the energy dissipation happens at the smallest cosmograph scale, the smallest eddies, which would still significantly larger than the molecular scale. Continuum. The smallest eddies are much larger than the molecular scales. Hence, the turbulent flow can be regarded as a continuum. Unlike the laminar flow, in turbulent flow, the flow can be separated into two parts. The main flow, the averaged flow, which is very similar to the flow in a laminar flow, and the fluctuating part of the flow, which is the unsteady part superimposing on the mean flow. Mathematically, the turbulent flow velocity, Ui, can be expressed as this. The mean part, the capital Ui, and the fluctuating part, U prime I. Here I equals to 1, 2, 3 for 3 different spatial directions, X, Y, and Z. If we take the capital U as the mean flow, and then we can easily obtain the average of the fluctuation part of the flow velocity is 0. Similarly, we can make the operations on the turbulent pressure, which can be regarded as a combination of the mean pressure, the capital P, and the fluctuating part, P prime. So we have this and this. To make the problem simpler, we consider the incompressible flows. Hence, the continuity equation can be expressed simply as this in Einstein summation. It is equivalent to this. Here, the double subscript I means the repetition from 1 to 3, given as this. So if we averaging the expression as this, we have this, and then average each term of the left-hand side of the equation. Since this term can be expressed as this, the average of the mean velocity is the same as this, and this can be replaced by this mean velocity and the mean of this term. So this will be 0. Hence, we have the continuity equation for the mean flow velocity as this. Accordingly, we would have the continuity equation for the fluctuating velocity as this. Having said the irregularity and the chaotic motions in turbulent flows, it is accepted that the turbulent flows are still governed by the Navier-Stokes equation. For simplification in this talk, incompressible flows are assumed. Thus, the Navier-Stokes equation can be given as this in Einstein summation. So we take the average of the equation, we have the expression as this. So for the linear terms, the averaging operations would be very straightforward as this on the velocity time rate and on the pressure gradient and the term for the viscous force. While the body force Fi is normally well described. For instance, the gravitational force, it would be same for both turbulent and laminar flows. The significant difficulties come from the nonlinear term in the moment equation, the convective term. As this, we substitute the mean and fluctuating velocities into the expression, and the averaging of the terms as this. Since the mean value Ui and Uj are constants for the averaging operation, therefore we can take them out. So we have the expression as this. Now the gradient of the fluctuation velocity with xj, its average would be 0. And obviously this term would be 0 as well. So all these two terms will vanish. Therefore, we have the expression for this nonlinear term. And we can see there is an additional term because of the flow turbulence. So we can write this additional term in this form. And if we apply the continuity equation for incompressible flows at this, and this term will vanish. Therefore, we have the expression at this. We write this back to the momentum equation. We have the expression for the mean velocity at this. Here is the additional term. Now, if we define a new stress tensor for the turbulent flow, Tij at this, and this term is named as Reynolds stress. So use the new defined stress tensor Tij. The moment equation for the mean flow velocity Ui would be given as this. This is the same as the moment equation for the nominal flows. In this slide, a discussion would be made for the Reynolds stress. Given the turbulent stress expression as this term represents the fluid viscous stress, and this is the Reynolds stress. From the expression, we can see Reynolds stress is the symmetrical tensor with 6 unknowns involving in Reynolds stress. Reynolds stress is a very difficult and challenging term, and generally there is no rational method to determine the Reynolds stress in analytical or numerical solutions for Navier-Stokes equation. For the flows of high Reynolds number, the Reynolds stresses are generally more important than the real viscous stress, since the viscous stress is proportional to the viscous coefficient, mu. It is inversely proportional to Reynolds number. Due to the Reynolds stress, the level of the total stress in turbulent flow is increased, which implies the friction drag on a body immersed in the turbulent flow will be larger than that in the nominal flow. A physical explanation for this is the turbulent momentum convection would cause the velocity profile to become more uniform, and therefore it will result in a larger velocity gradient near the boundary. Here in the plot, we can see the turbulent and nominal boundary layer over a flat plate with free stream velocity u0 equaling to 55.56 meters per second. So here you can see the large gradient for the turbulent boundary layer, therefore a large skin drag in the turbulent boundary layer. For a simplification of the problem, the turbulent boundary layer on a flat plate is discussed here. The problem analysis would show the mean velocity u in the boundary layer given as this. Here, the normal u is used for the mean velocity in the boundary layer rather than the capital U. So we can see the velocity distribution would be a function of the parameters of boundary layer thickness delta, the distance from the boundary y, the fluid density rho, the fluid viscosity mu, and the free stream velocity u0. However, in the analysis of the turbulent boundary layer, the free stream velocity u0 is normally replaced by a so-called friction velocity u tau, which is calculated as this, given by the shear stress on the boundary. This replacement can be justified since for a given u0 and a fixed x, there will be a unique value for shear stress on the wall tau 0. Thus, the unique friction velocity u tau. So after the replacement, we have the general expression for the velocity distribution as this. We can make a dimensional analysis to this expression, and that would lead an expression as this. The non-dimensional velocity distribution u with regard to u tau is given by a function of two non-dimensional parameters. The first parameter is the Reynolds number based on the friction velocity u tau and the distance from the boundary y. And the second non-dimensional parameter is y divided by the boundary layer thickness delta. As the main parameter for the boundary layer, we can assume that the non-dimensional velocity within the boundary layer is a function of the Reynolds number u tau y divided by nu, while the non-dimensional parameter y divided by delta would be used for completing the formulation of the boundary layer. As such, we have the expression for this non-dimensional velocity u as the function f1. So if we apply the boundary condition, we have on the boundary where y equals to 0, and the no-slip boundary condition would lead f10 equals 0. And also, we can calculate the shear stress on the boundary tau 0 given by this, and we can calculate the differentiation of the velocity with regard to y as this, and then we have the expression as this. This equation would lead to an expression as this: f1 prime 0 equals to 1. Here, the prime denotes the derivative with regard to its own argument of the function. So if we put all this together, we can have an approximation for the function f1 as this. This expression is valid for the viscous sublayer, where the Reynolds number based on the friction velocity and y is smaller than 5. Outside the viscous sublayer, there might be a certain region within the boundary layer where the non-dimensional parameter y divided by delta would be important. Based on this deduction, we can assume a velocity defect law as this expression. So this velocity defect law can be understood at the certain region outside the viscous sublayer. The moment flux may be balanced by both viscous stress and the Reynolds stress. Thus, the velocity defect u0 minus u is used in the expression. The velocity defect law means that the defect velocity in the certain region within the boundary layer would be a balanced result by both the shear stress on the boundary, thus the friction velocity u tau, and the non-dimensional boundary layer parameter y divided by delta. In seeking the solution for the boundary layer, we can assume in certain region within the boundary layer, these two functions, f1 and f2, are both valid for approximation of the boundary layer. So, we could formulate the equation as this. This assumption has been proven very useful for solving the boundary layer problem. It is generally assumed that the Reynolds number based on the fraction velocity and the boundary layer thickness delta is significantly larger than a unit given by this. Now we take the differentiation of the equation with regard to y and multiply y on both sides. We have the expression as this. From this equation, it can be seen that in both sides of the equation, there are functions of the long-dimensional parameter u tau y divided by nu and y divided by delta, respectively. As such, the equation holds correctly if and only if they both are a constant a given as this equation. Now we can integrate the first equation, so we have the function f1, and integrate the second equation, we have the function f2. Both c1 and c2 are the constants of integrations. And use the experimental data, we can decide the constants in this expression. Here we have a equals to 2.5, c1 is 5.1, and c2 is 2.35. And kappa equals 0.41, roughly equal to the inverse of the constant a. Kappa is the von Karman constant used in fluid dynamics. Therefore, we have the expressions for the boundary layer, and these equations can be used in different regions within the boundary layer. So in this figure, we can see the standard turbulent boundary layer formulation gives very good agreement with the experiment data. According to Newman's book, Marine Hydrodynamics, there are more data are available, and the experiment data include the boundary layer profiles for flat plate, as well as the tubes and the channels. All these boundary layers are same. A simple and very popular turbulent boundary layer profile is the 1/7 Paul law, which was proposed by Planter and correlated by Brasius using the experiment data. If you want to know more how this 1/7 Paul law is derived, please read the book Aerodynamics for Engineering Students. The 1/7 Paul law is given as this, and this 1/7 Paul law gives very good agreement with the experiment data for the Reynolds number Rx smaller than 10 power of 7. However, there is an obvious drawback of the formula, since it would lead an infinite shear stress on the boundary. A direct calculation for the shear stress on the boundary given by this. Here, when y equals 0 on the boundary, it is infinite. So, alternatively, we have used an approximation which was derived from the standard boundary layer we talked in the previous slide, the logarithmic boundary layer. It is given as this, tau 0. So if we draw the 1/7 power law against the experiment data for the turbulent boundary layer, we can see for different Reynolds number from 100,000 to 10 million, we can see this 1/7 power law gives very good approximation to all this turbulent boundary layer profile. And in this plot, we also draw out the laminar boundary layer, the Brazier's solution, and the parabolic approximation. So all this data for this drawing from the book Fluid Mechanics, FM White. Based on the 1/7 power law of the turbulent boundary layer, we could have the following approximations. The turbulent boundary layer thickness is given by delta equals 0.373x Rx power of minus 1 of 5. Here, the Reynolds number Rx given by this. So from this expression, we can compare the boundary layer thickness to the laminar boundary layer thickness. It can be seen laminar boundary layer thickness is proportional to x square root. This is the laminar boundary layer thickness expression. The turbulent boundary layer thickness is proportional to x power of 4 divided by 5. Therefore, turbulent boundary layer thickness grows much faster than the laminar boundary layer thickness. So in this plot, we assume the free stream velocity u0 equals to 55.56 meters per second. And this is the laminar boundary layer thickness, and this the turbulent boundary layer thickness. So we can see the turbulent boundary layer thickness grows much faster than the laminar boundary layer thickness. And the turbulent displacement thickness given by delta star at this, the momentum thickness theta at this, and this is one important parameter, the shear stress on the boundary tau 0 given by this. This is very important because when we need to calculate the friction velocity u tau, we must calculate tau 0 first. So this is the formula we might use for calculating the shear stress on boundary. We have talked about the basis of the turbulent boundary layer, and this could provide the standard wall functions for CFD applications, such as commercial software, ANSYS Fluent, and the open source OpenForm. In ANSYS Fluent version 18, the available wall functions include standard wall functions, scalable wall functions, equilibrium wall functions, Mentor-Machner method, and also has an option for users to define their wall functions. In OpenForm, the available wall functions include epsilon wall functions, KQR wall functions, omega wall functions, F wall functions, NUT wall functions, and V2 wall functions. And for all these wall functions, they may also have the corresponding wall functions of low Reynolds number. If you want to know more information about the wall functions, please read the paper, a thorough description of how wall functions are implemented in the OpenForm. This paper is available online, and you can download it.